I'm Brian Thornberry, and today I'm going to teach you how to code the algorithm DeepQ Learning released by DeepMind in their 2015 paper, Human Level Control Through Reinforcement Learning. This video is part of a series where I'm going to teach you how to code the more advanced algorithm Rainbow, released in 2017. This video is primarily intended to be technical, so we can understand the algorithm and implement it in code. Also, I highly recommend you have experience using both Python libraries, NumPy and PyTorch, which is what we're going to be using to implement DeepQ Learning today. However, this is not a requirement because technically you could just copy the code that I'm writing and have a working implementation of DeepQ Learning. To get the most out of this video, I highly recommend you take the time to understand what's going on in the code. Pause if necessary, go read, or do little experiments so you can understand what each part of the code is doing. Okay, before we dive into the code, let's do a brief overview of the paper and algorithm. Here we have the paper, Human Level Control Through Deep Reinforcement Learning, released by DeepMind in 2015. This paper introduced the DeepQ Learning algorithm. We're going to go over a few different parts of this paper, but before we do, let's take a moment to understand what is Q Learning. I found this great graphic courtesy of analyticsvidya.com that gives a basic overview of what we're talking about. Q-learning was an algorithm invented sometime in the 90s, and up until recently, actually up until DeepMind released this paper, people believed that it did not work properly with neural networks. So deep Q-learning is the fusing of Q-learning with neural networks to estimate what's called the Q function. The Q function is very simple. It takes in any given state of the environment and returns what's called the Q value for each possible action the agent can take in that environment. The Q value is the expected reward from all future states in that environment, given that we take that action. To understand what that means, let's take a look at how the neural network interacts with the rest of the reinforcement learning system. So the neural net predicts the Q value for each particular action given the state. In this case, there's three different actions that we can take in this environment: speed up, no change, speed down. We use what's called an epsilon greedy policy to select an action with the highest Q value, or sometimes just a completely random action to facilitate exploration and learning about the environment. We take the action by sending it to, in this case, the simulator, and the simulator updates its state based on that action and returns a reward. You can think of this as the score in a game, but in practice, it can be many different things. At the same time, the simulator returns a new state that the neural network takes back in and repredicts the new Q values, and the loop begins all over again. Now, how the neural network updates its parameters based on this reward is the crux of the Q learning algorithm and what we're going to go over in the paper. Okay, back to the paper now. We're going to briefly go over this. We're not going to take the time to go through the whole paper. We're going to go through a couple of the highlighted portions here that I think are important, and then we're going to take some time to understand the algorithm before we code it. So right here, this is the core equation of Q learning. This is how it learns from the rewards returned by the environment. If this looks like Greek to you, don't worry about that. It did the first time I ever saw it too. And we don't need to really understand this to implement the algorithm. So let's go ahead and go down and keep going. So right here, what I want to show is a couple different examples of why it's important to actually read the paper before you implement these algorithms. So right here, you can see that they detail the neural network architecture that they use. Additionally, you can see that they clipped all positive rewards at 1 and all negative rewards at -1. And they also use frame skipping, so that the agent only sees and interacts with every 4 frames. These are just a couple examples of the many different implementation details in this paper. We are actually not going to use this neural network architecture or a lot of these implementation details in our implementation because we are not going to be training the agent to play Atari games, in this video at least. Scrolling down, we come to the most important part of the paper, training algorithm for DeepQ networks. This section gives us all the details we need to actually implement the algorithm. Before we dive into the algorithm, let's take a moment to examine this part right here, where they talk about how they clip the error term between 1 and -1. Now, the internet is divided on how to interpret this statement. If we go to Stack Overflow, we can see that the consensus is to actually clip the gradient between -1 and 1, not the loss function. If we look at the actual implementation that DeepMind released, we can see that they do actually clip the error term, which is delta here, between 1 and -1, exactly what they say they do. But if we look at newer implementations of the algorithm, such as the one from OpenAI baselines, we can see that they use a Huber loss, which changes from the squared error to the absolute error when the loss is greater than or less than -1. In our implementation, we're going to use the Huber loss. I've tested it and it works well. This is just an example of how papers can be ambiguous and interpreted differently, so it's important to do your research if something strikes you as ambiguous. Now onto the algorithm. I'm going to explain what each line means right now, and then we're going to dive straight into the code. First, we initialize the replay buffer to its full capacity with random experiences. Then we initialize what's called the onLine queue function, followed by the target queue function. The differences between these will become more apparent in a moment. Then we step into our loop, reset our environment to get our initial raw state, and then pre-process that state with our environment wrappers. We actually won't need to do any pre-processing in our implementation since we won't be training on Atari games. Then we step into our core training loop. We select the action with the highest Q value given the current state, or with probability epsilon, select a completely random action. This is the epsilon greedy policy I mentioned earlier. Just a reminder, all of this will become more clear once we start coding it. Then we send that action to the environment, which returns a reward in a new state. We store that state inside of the replay buffer, and we're actually going to need to add an additional element to this tuple here, telling us whether or not it's a terminal state. At this point, we get a random mini batch of transitions from the replay buffer. We compute our targets based on those transitions, and then perform the gradient descent step on those targets. And right here, where it says squared, this is another great example of where papers can be ambiguous, since they don't actually include the error clipping inside of this algorithm. So as we implement it, it will actually be slightly different, since we won't be squaring the error term. Then every C steps, we set the target network parameters to the online network parameters. The online network parameters are what have been being updated by the gradient descent step. Okay, now let's dive straight into the code. You can see I'm using PyCharm. You can go ahead and use whatever IDE you're comfortable with, although I highly recommend PyCharm. But in the past, I used to use VS Code and it worked just fine. So I already set up my project here since it took a little bit to install the dependencies. But the primary thing you're going to want to do is create a virtual environment, and then you're going to want to run pip install torch gym. And that's going to go ahead and install PyTorch and OpenAI Gym, which are our two dependencies for this project. Now, as you can see, I already have them installed in mine. So we're going to go ahead and get started. Create a new file, DQN.py. Okay, so just to start off, we're going to create a few hyperparameters here. Okay, now that we have those typed up, let me quickly explain what each of these are. Gamma is our discount rate for computing our temporal difference target, and we'll see what that is a little bit later in the code. Batch size, this is how many transitions we're going to sample from the replay buffer when we're computing our gradients. Buffer size, this is the maximum number of transitions we're going to store before overwriting old transitions. Min replay size, this is going to be how many transitions we want in the replay buffer before we start computing gradients and doing training. Epsilon start, this is going to be the starting value of our epsilon. This is going to be the ending value of our epsilon. And this is the decay period, which the epsilon will linearly anneal from this value to this value over this many steps. Target update frequency is the number of steps where we set the target parameters equal to the online parameters. Now we're going to see exactly what all that means as we get a little further in the code. Now, before we dive into the rest of it, let's get our imports typed out. Okay, so if you're following along the video, just go ahead and pause it and get those imports typed out. And we're going to continue on here. So the very first thing that we need to do is create our environment. And we're going to be using the CartPole environment because it's an environment where we can iterate quickly and find out whether or not we have a correct implementation of deep Q learning. Okay, so we create our replay buffer, which is just the standard deck from Python, the max length buffer size. And we're also going to create a reward buffer where we store the rewards earned by our agent in a single episode. And we do this to track pretty much the improvement of the agent as it trains. Let's keep track of the reward for this specific episode. And if you guys are familiar with Gym, then you'll know that there are definitely better ways to do this with the monitor, but we are pretty much doing a vanilla implementation here without too many fancy things. Okay, for the next step, we need to come back up here and create our network class. And in PyTorch, you do that by creating a class which inherits from nn.module. And we initialize the class, calling the superclass. We compute the number of inputs to this network by taking the product of the observation space shape. Now, in this particular environment, CartPole, taking the product is actually not necessary since we already have a one-dimensional space. But in other environments, such as the Atari games, this is going to be a three-dimensional shape for the images, or in other environments, possibly even more dimensions. So that's why we have this generalized product here. So this is essentially how many neurons are in the input layer of our neural network. For the rest of the network, we're going to use a standard 2-layer sequential linear network with 64 hidden units. Right there, so separated by a tan H nonlinearity, and the number of output units in our network is going to be equal to the number of possible actions that we can, or that the agent can take inside of that environment, which is this env.actionSpace_n. Now, quick note here, Q-learning can only be used with action spaces that have a finite number of actions, called a discrete action space. Other environments with continuous action spaces require different algorithms. Okay, we do our forward function, which every single nn.module is required to implement. And we're going to just put this placeholder here for now. We're going to come back and fill it in a minute. And that's the act function. We'll see what that does in a moment. Okay, now we can come and create our networks. We're going to create our online net and our target net. And I forgot to pass the env in here. No, that's good. Okay. Now we set the target net parameters equal to the online network parameters, and they'll both have been initialized differently, so that's why we have to do this. And this is part of the algorithm as specified in the paper. So now the first step is to initialize our replay buffer. And what we're going to do, remember that constant min replay size, we are going to put that many transitions inside of the replay buffer before we even start. So first thing, we reset our environment, get our first observation. We loop min replay size times, and then we select a random action by calling the actionSpace.sample method. Looks like I made a little mistake here. Forgot the in. Next thing, we need to step the environment with that action, and as a result, we get out the new observation, which is the state of the environment, in case I didn't explain that a moment ago. And we get out this other information, which is the reward returned by the environment for that action whether or not the environment episode is done and the environment needs to be reset, and the info dictionary, which we're not going to use at all, so we'll just go ahead and replace that with the underscore. Now we create our transition tuple, just the obs, the action, the reward, done, and the new observation, and we stick that inside of our replay buffer, just like that. So now we have that experience inside of our replay buffer, which we can use to train on later. Never forget, set obs equal to the new obs. And if the environment needs to be reset, reset it. And always get the new obs out of that reset. Okay, now we're getting to the exciting part, which is the main training loop. Do the same thing here, reset our environment, get the observation, and we're going to count which step we're on. This is pretty much like a while true loop, but instead we get the count using this itertools.count method. Okay, so the first thing we need to do here is select an action to take in the environment. But remember, we're using the epsilon greedy policy. So we need to compute epsilon for this step since it interpolates between the epsilon start and epsilon end values over epsilon decay steps. And numpy has this really handy function np.interp, which we can use to do just that. And what this is going to do, this is going to start out at epsilon start and end up at epsilon end after epsilon decay steps. And for every step after that, it'll still be epsilon end. Okay, so remember, this is 1.0 and this is 0.02. So that means we're going to go from 100% random actions to 2% random actions. And this is done to facilitate exploration by the agent in the environment. So we get a random sample. If the random sample is less than or equal to epsilon, then we take a random action using the actionSpace.sample method once again. However, if it's not less than or equal to epsilon, we need to intelligently select an action using our network. So we're going to call onlinenet.act. We're going to pass in the observation here. So we're going to go back and fill that in just a moment. Before we do, let's go ahead and copy this entire code right here from the initialize replay buffer section and put that right here since it's exactly the same. Remember what we're doing. We're stepping the environment. We're getting all the new data, the reward, whether or not it's done, the new observation, setting up the transition tuple, putting that in the replay buffer, always setting obs to new obs, and resetting the environment if it needs to be reset. But we need to do a couple other things here besides resetting the environment. We need to append the episode reward to the reward buffer, and we need to reset the episode reward. Which reminds us that we need to come right up here and add the reward for this step to the episode reward. Now let's go back up and fill in that act function before we move on any further. First thing we need to do, we need to turn obs into a PyTorch tensor. Just like this. Called torch.asTensor. Make sure to pass in the D type. And I always put this underscore T so I know that this is a torch tensor. Next, we need to compute the Q values for this specific observation. And a quick note here, we have to put the unsqueeze 0. And that's because every single operation in PyTorch expects a batch dimension. And since we're not using any batched environments, we don't have a batch dimension. So we just create pretty much a fake batch dimension of size 1 with the unsqueeze 0. Okay, now we have the Q values. for every single possible action that our agent can take. We need to get the action with the highest Q value. And we do that using torch.argmax. Just like this. And that's it. In the action, we need to turn this PyTorch tensor here into an integer. So that's pretty simple. We just detach the tensor and then call .item. And now we have the action indice, which is just a number between 0 and 1 minus the number of actions. And that's what we can return as the action. So that's how we select an action in Q-learning. Now we move on to the next part, come all the way down here, and we're going to start our gradient step. Now I'm going to type this all out real quick and then I'll explain it. Okay, so what we've done here is sample batch-sized number of random transitions from our replay buffer that we added in earlier. And remember, the transitions are all structured as this kind of tuple, but we need each of these elements individually in their own arrays. So that's what we've done here. We get each observation and put it in a list from these transitions we sampled. And then we call np.asArray. And the reason for doing this, even though it might seem like a waste, as you'll see a little bit later, is because PyTorch is much faster for making a torch tensor from a NumPy array than it is from a Python array, as I have known from my own experience and mistakes. Okay, now we need to convert each of these into a PyTorch tensor. It's going to be very simple to do, especially if we have multi-line edit. Go back to the beginning here. Our underscore T. And one more thing. Actions is actually an int 64 since it's an index, really. Okay, now we have all these PyTorch tensors. We're ready to start computing our targets for our loss function. So first thing, we need to get the target Q values for the next or the new obses. And this is the first time where we're using the target net. Now imagine that for each of these new observations, we have a set of Q values. But what we need to do is we need to collapse this down to one highest Q value per observation. And we do that like this. Okay, so let me conceptually explain what this is doing. Right here, we have a set of Q values for each observation. And we can say that each observation is essentially the batch dimension and the Q values are dimension 1. So what we're telling this is get the maximum value in dimension 1 and discard all the rest and keep that dimension around even though there's only one value in it. And then we do the 0 index because max returns a tuple where the first element is the highest values and the second element are the index of those values, which is equivalent to argmax. Now we're ready to compute our targets. I'm going to type this out and explain it afterwards. Now to quickly show what we've done, computing the targets essentially computes this function right here from the paper. Back to the code, what we've done is we take the rewards plus gamma times the max target Q values, except if that particular step is a terminal state, then we will zero out this entire portion and it will be only the reward. So that's a clever way of computing this piecewise function in one step. Now we're ready to compute our loss and apply our gradients. We get the Q values from our online net for the ops, and then we get the Q values for the action we actually took. And let me explain this after I'm done typing it. So what we've done here is, once again, we have a set of Q values for each observation, except this time we're not getting the max. What we're doing is we need to get the Q value for the actual action that we took in that transition. We do that using this torch.gather method, which applies this index in this dimension to all of the elements of this tensor, and effectively gives us the currently predicted Q value for the action we took at the original time of the transition. So now we compute our loss, and we use the Huber loss, like I mentioned before, and that is this called smooth L1 loss in PyTorch, and it's done just like this. And by the way, the order of these does supposedly seem to matter. I haven't really tried switching them around, but just a heads up there. We do our actual gradient descent step. First things first, we zero out the gradients. And it looks like we forgot to create our optimizer. So we're going to come back all the way up here right after we create the networks, and we're going to create our optimizer. So that's torch.optim.atom using the atom optimizer. We optimize on the online network parameters, and we set our learning rate 5e-4. And this really should probably be a constant up at the top here, but for the moment, we're just going to leave it. Now we're back down here. You call loss.backwards to compute our gradients, and optimizer.step to apply those gradients. A couple more steps here. We need to remember to update the target network every target update frequency steps. Very simple to do using the modulo. And this load state dict function will set the parameters of the target net to the same exact values as those in the online net. Let's not forget to do our logging so we can see if things are actually improving. Print out the current step. And we'll print out the average reward from our reward buffer over the last 100 episodes. Okay, now let's go ahead and just do a smoke test. I'm just going to run it and see whether or not it seems to be improving. Oh, looks like we made a mistake. Forgot 2 underscores on the init function here. We made another mistake. We accidentally typed 65 here instead of 64. These little mistakes are extremely common when you're programming AI, and they'll probably happen to you as well. Just try not to get bogged down by them. And it looks like we have another mistake, and that's right down here where we are doing the torch.gather, and there's something wrong with the index, and I realized that's because we forgot to put the batch dimension on a couple of our arrays here, our tensors. And notice that we're using unsqueeze -1 instead of unsqueeze 0 as we did up here in the act function. And the reason for that is because up here, there's no batch dimension. We only have one observation. So we want to pretty much create a fake batch dimension. But down here, we have already batch size number of actions. And that effectively is the batch dimension. And what we want to do is we want to get each of these values inside of its own dimension. That's why we call unsqueeze -1 to add a dimension at the end rather than at the beginning. Now let's go ahead and run it again. And it appears to be going. It looks like tough to tell if it's improving. We'll let it run for a few steps here. And this is when it's always useful to have a baseline, when you can go and run someone else's code with the same exact hyperparameters, running the same exact supposed algorithm, and just see watch the pattern of how it improves or doesn't improve. And it's extremely valuable because while you're sitting here watching this, you can get these extremely frustrating results where it seems to be improving and then doesn't. And in my case, once I actually had, the first time I implemented DQN, I had a tiny bug in the program that would sabotage the results about halfway through the training, and it would just go all the way down to 0. And it took me about a week to find, 7 days. And it was terrible. But, that's part of AI, is kind of finding these tiny little bugs and part of getting better. Okay, this appears to be improving just fine. If we let this run, it will solve the program. So you can see here, we have a working implementation of DeepQ learning. Now I want to go ahead and add in one more component before we let that solve. And that's going to be right here. And this is a really simple component. After it's done solving it, we just want to watch it play instead of just staring at the numbers. And this is really cool, really rewarding after, you finally got this working and you can actually see it playing the game. So what we do here, if we have at least 100 episodes and the mean of our reward buffer is at least 195 and the maximum score is 200 in CartPole v0. So just to clarify that, we just go ahead into this infinite loop here to ignore the rest of the code, select an action. We ignore most of this, but we still need the done. Step the environment. Render the environment, which is the fun part. And remember to reset the environment. Now let's run it, and when it's done, I'm going to speed this up here. When it's done, we're going to get to see it play. Okay, wow, look at that. It's playing and it seems to be solving the game. And we can come and take a look at what it does randomly to see how different it is. So if we just go ahead and exit out of this and stop our training here, and we just go straight into this loop just for demonstration's sake to see exactly how much it has learned. We can see here, it just ends the game every single time because once this thing gets up to a certain angle, it assumes it has lost. So you can see it's not doing anything at all. It's completely random, actually. Okay, and that's that. Now we have the working implementation of DeepQ learning trained on the CartPole environment. Now I want to come back up here and make a quick note before I end, and that is about these hyperparameters. These hyperparameters are going to be different, especially in this variant of DeepQ learning, for every single environment. And I got these exact hyperparameters from the OpenAI baselines example of their solution of CartPole. And if you go ahead and look in the paper and you scroll down, they have a list of all the hyperparameters they used in their solutions of the Atari games here. So that's all. I hope you tune in for the next video, where we're going to be continuing on with DeepQ learning, and we're going to take it all the way up until we've implemented the popular rainbow algorithm, one of the most sophisticated variants of DeepQ learning today. Thank you for watching and making it this far. Remember to like and subscribe. We've got a lot of great videos and more algorithms besides DeepQ learning coming even after this. Have a great day.